Good afternoon. I will summarize three connected parts of my research fellow work: a grid digital twin, realistic customer demand, and grid-aware EV planning. These tasks from one workflow. The digital twin provides the network, clustering and generation improve the demand input. EV planning then combines transport demand with grid limits to support investment decisions. My first task was power grid digital twins. The project pipeline converts feeder data into Power networks. Power is an open-source power system tool that integrates power grid design tools and power flow solvers. Node become bus, conductor become lines, and substations become load. In Brick Hill, 6 feeder data sets connect with the address level model. This let us place future load, solar, battery, or EV scenarios on the physical topology before testing them. At each simulation step, the service receives active power for every bus. Power run AC power flow and return a per unit voltage for every bus. The system compares the results with the study limits. It can therefore identify possible undervoltage or overvoltage before future operating plan is accepted. I made the solver reusable. A project can upload a Power JSON file, enable a network, send bus injections, and receive bus voltage through one API. Multiple datasets can be saved. Will each request use a safe copy? Docker and Azure deployment scripts make the same component portable across machines and projects. My second task was load demand cluster and generation. I combined half-hourly net load with household, solar, and appliance information. This produced 62 features for 5,000 customers. I tested 6 to 14 clusters and compared k-means performance. The selected model has 6 k-means groups because the data in each cluster is not far from the central point. I describe them as potential categories, not real household labels. Next, I build cluster-specific generators for clusters with enough data. I use LSTM autoencoders with calendar information and losses for shapes and peaks. For sparse appliance data, I use controlled smooth noise, preserving zero and delay peaks. The profiles support future scenarios when data is limited. My third task was AV infrastructure planning from mixed road traffic. The input include light and heavy vehicle counts. But the current model aggregates these classes before creating hourly charging demand. It builds low, middle, and high scenarios, then combines them with potential location, charger types, costs, and feeder data. The model is mixed integer linear program. It selects the location, charger mix, connection capacity, demand assessment, and unmet demand. The objective minimize annual investment and operating cost, include penalty for unmet demand and additional charging trip. Constraints cover at least 85% service, charger and connection limits, and the bus voltage limits. Power then run an independent bus voltage check to make sure no voltage violations. This design grows with demand. EV10 need 62 kilowatts, EV20 need 123, and EV50 needs 290. At EV50, one charging station with 16 chargers serves 98.8% of the high demand case, and about $230,000 modeled capital cost. In the voltage check stage, no bus voltage below 0.95% per unit. In summary, the main work of my research fellow is model the network, improve demand data, and plan investment within grid limits. Thank you.